Hey everybody, welcome back to astronomy. Last time we were talking about supernova remnants. Specifically, we're talking about neutron stars, and we said that if a neutron star is too massive, if it's more than about 3 times the mass of the sun, even the repulsive force between the particles inside of a neutron is not enough to fight that gravitational collapse away. And then that object, if it's that leftover neutron star, if it's too big, will become this thing called a black hole. And we can't really understand why a black hole is even possible until we understand a little bit about our modern theory of gravity. So I have some slides here to review, so let's review them really quickly. We said that a neutron star is an object that is about as massive as a star, about as massive as the sun. Stars are all different masses, but about a 1 solar mass, maybe a little bit less. But it would fit comfortably between Chester and Petersburg. It's only about 5, 10, 15 kilometers across. And the question we want to ask is, well, what happens if a neutron star is so heavy that it collapses even further? What happens to the matter that makes up that neutron star? So what is the idea of a black hole? The idea of a black hole is it is an object that is so small that escape velocity is equal to or greater than the speed of light. Escape velocity is a pretty straightforward concept. Every object has a gravitational pull. The escape velocity is how fast you have to be going to get away from that object and never come back. So the escape velocity of the Earth is 11 kilometers per second. If you shoot a rocket up at 11 kilometers per second, it will keep going and it will never come back. People asked actually a long time ago, way before Albert Einstein, is it possible to imagine an object whose escape velocity is greater than the speed of light? So you would have to be going greater than the speed of light to get away from it. If that was true, then light wouldn't be able to escape from it, hence black hole. But it wasn't clear before Einstein, before the 20th century, if light should be affected by gravity at all. What is gravity? We talked about at the very beginning of this course, the wrong idea of Aristotle about what gravity is. Aristotle thought gravity was a natural tendency of objects made of earth, like this metal ball, to want to go back to the place in the universe where they belong, which is the center of the universe. That what made something move in a particular direction had to do with what it was made out of. That is wrong. Galileo came along and showed that different objects don't fall at different speeds depending on how much earth they have in them, that a 1-pound rock and a 10-pound rock, if you drop them, will actually fall at the same speed. So this idea that what makes a 10-pound rock heavier is that it wants to get to the ground more is just wrong. Galileo, what he didn't do was provide us with anything better. He showed us what Aristotle was wrong about, but he didn't explain what gravity was. Isaac Newton came along in 1687 in the Principia and published a notion of gravity, that gravity was an attractive force between any two objects in the universe. I asked a question in one of the little online quizzes a few weeks ago, which is, what was so special about Newton's discovery? Didn't we know that things fall already? Sure. It wasn't just that things fall because of gravity that Newton discovered. Newton discovered that the force that attracts this rock or this metal ball to the Earth is the same force that holds the moon in orbit around the Earth, and the same force that holds the Earth in orbit around the sun, which is the same force that holds Jupiter's moons that are in orbit around Jupiter and Saturn's moons in orbit around Saturn. In other words, there's one attractive force between every object in the universe and every other object in the universe, and that is the force of gravity. And we can quantify it. The force of gravity between two objects is the mass of the one object times the mass of the other object divided by the distance between them squared times this little constant called G, which is sort of a measure of how strong gravity is in our universe. Gravity is actually a very, very weak force. We only notice gravity. Like I can't feel the gravitational attraction between these two balls. They don't feel like they're gravitationally attracted at all. They are, but with a force of a billionth of a Newton, a force too small for me to feel. You don't notice the gravitational attraction between you and anything in the world but the Earth. Why? Because the mass of the Earth is really, really, really big. So we can calculate the gravitational force between any two objects in the universe. What Newton did not do, however, was explain why there is a force of gravity between the Earth and the moon, or the moon or you in the Andromeda galaxy or whatever. And he didn't explain how it worked. In other words, what actually is physically happening between the Earth and moon that causes them to be pulled towards one another. Because that's weird, right? The moon's really far away. There's no invisible rope connecting the Earth to the moon. What is going on in space between the Earth and the moon, or between the Earth and you, or between the sun and Jupiter, or between the Milky Way and the Andromeda galaxy? What is going on there that causes that attractive force? Newton didn't try to explain it. The fact that he didn't try to explain it was actually really, really important in the history of science. Aristotle tried to explain everything. Everything had to have a reason. Science, or philosophy of nature, was about providing reasons why everything happens. Newton was like, it doesn't matter if we don't understand the reason why gravity happens. Here is a bunch of equations that you can use to predict how things will move. And that's all you really want. I mean, you might want to understand why, but the most important thing is to be able to understand and predict what nature is doing, which Newton's law of gravitation lets us do. Putting the mathematical description ahead of the philosophizing was one of the most important things that Newton did. It established science as a way of quantifying the universe first, and then the explanations come after we have come up with those predictive theories and models. Really, really important. But it's still unsatisfying not to know what causes gravity, right? What makes this gravitational attraction happen? For what, Principia was 1687. So from 1700 to 1900, that's 200 years. We were able to describe how the planets move, and comets and asteroids and moons go around the planets. And we were able to write down equations predicting why all those things happen. And those equations work super well, but nobody had any description for why that gravitational attraction happens. That explanation will not come until the 20th century with Albert Einstein's theory of general relativity. We don't really have the time to kind of walk through the steps of how Einstein hit upon this idea. It's super interesting stuff and super important stuff. And knowing what relativity is about is actually more important than what I'm talking about today, which is kind of the results of relativity. If this was a physics class, we'd probably spend 2 whole days talking about the history of relativity and how Einstein came up with these crazy ideas. He didn't just pull these ideas out of thin air. Einstein didn't just sit down at his desk one day and say, I think that nothing can travel faster than the speed of light. And when you go to the speed of light, the clocks slow down, and space and time are relative, and gravity is a curvature of space. He didn't just make this stuff up. Einstein was trying to solve some very specific problems that were plaguing physics at the end of the 1800s. Chief among them was understanding light and how light worked. And one of the things to come out of this was a description of the effect of gravity on light. If we believe, oh, I don't want to do this. This is not the slide I thought was next. Hold on a minute. Yeah. Oh, maybe I do want to do that. So what does Einstein say is the cause of gravity? We'll do that first, and we'll talk about the proof of it. Einstein says that gravity is caused by a change in the geometry of space and time, that the presence of mass, quote unquote, curves space. And it is that curvature of space that changes straight line trajectories into curved line trajectories. In fact, the orbit, or the path traveled by an object that's experiencing gravity, is a straight line in curved space-time. What does that mean? It means that before Einstein, from Newton and way before Newton, all the way up until the 20th century, people thought of space and time as being separate from objects and motion and energy and matter, right? Space and time are there all the time, and matter and energy live inside of space-time and don't affect it. Newton actually is very clear about this in the Principia. He says absolute time of its own nature flows equably without relation to anything external, meaning time is time and it's absolute, and nothing that happens in the universe affects time. Einstein says that's wrong. And he didn't just say that because he was a genius and comes up with crazy ideas. He recognized it had to be wrong in order for our descriptions of light and electricity and magnetism to be right. And again, we don't quite have time to get into all the details of that. Likewise, space, what we think of as an amount of space, a meter of space, or a foot of space, or an inch of space, we think of that as just being a measurement of something entirely abstract that exists apart from rulers and objects that might be an inch in size. Einstein says, no, that's not true. Space and time are not just the stage on which physics happens. Space and time themselves are actors in the drama of the universe, and things affect space and time just like things affect matter and energy. And when you put matter and energy in space, that matter and energy affects measurements of space and measurements of time. And so what the sun is doing in our solar system is changing the geometry of space and time in such a way that the planets follow the straightest path they can through the geometry of the curved space-time that the sun creates, and that path is an elliptical orbit, not a straight line. I mean, not a Euclidean straight line. It's a straight line in non-Euclidean curved space-time. So Einstein says that gravity is a purely geometrical effect that's caused by massive objects changing the geometry of space and time. It's a really abstract idea. If it was the year 1750, and we pulled out our book of Newtonian physics, we pulled out our Principia, and we ask, what should gravity do to a beam of light? What would the Principia say? Well, the Principia says that the force of gravity between two things is the mass of the one thing times the mass of the other thing, m times m, divided by the distance between them squared, r squared, times this little number g, 0.000000000667. So if we ask, what force of gravity would the Earth exert on a beam of light? We plug in the mass of the Earth for the big M and the mass of the light for the little m, but the mass of light is 0. Light doesn't have a mass. Light doesn't weigh anything. If you plug a 0 into Newton's law of gravitation for one of the masses, you get that the force should be 0. So to strictly interpret Newton's laws, if light has no mass, it shouldn't really be affected by gravity. Now, it's a little more complicated than that because light does have energy, and Einstein's theory of special relativity from 1905 does say that gravity should affect energy. Let's not get into all the nuts and bolts of what relativity says. Suffice it to say that to naively take Newtonian physics on face value, to take his law of universal gravitation and apply it to a beam of light would suggest that light shouldn't be affected by gravity at all. But if Einstein says that what gravity is not a force between things, it is effect of the geometry of space being changed by the presence of a massive object. And what would Einstein say a beam of light should do? Einstein would say a beam of light should be curved because it's passing through curved space, space that has had its geometry changed by having matter and energy in it. So Einstein's theory of gravity would predict that light should be affected by gravity, whereas Newton's, naively anyway, would predict that it shouldn't be. Well, somebody had to test this idea. Einstein's ideas were really powerful and explained a lot of stuff, but that doesn't count for anything if they're not right. So we had to test it. What are we testing? We're testing, is light actually bent by gravity? Well, what would we need to do that? We need something really, really massive with enough gravity to bend a beam of light. Well, if we look around us, there's really nothing available that has that much gravity, except for the sun. The sun's the most massive thing in our area. But we can't look at sunlight because sunlight is coming from the sun. We have to look at light that's coming past the sun and see if that light is deflected. So we have to, for example, look at the light from this star as it goes past the sun and see if that light is bent. Well, you can't look at light from a star that goes past the sun because you can't see the stars when the sun is out. The sun is too bright. Except for very rare occasions when the sun is blocked out, like an eclipse. Einstein published his theory of general relativity around 1915, 1917. Shortly after, in 1919, there was supposed to be an eclipse of the sun. And scientists decided that if they photographed the stars near the sun during that eclipse, that they should be able to notice the sun's gravity distorting or warping the path of the light from those stars. In other words, if we imagine the light from those stars coming past the sun, if the sun's gravity does affect light, the path of that light will be bent. And if the path of that light is bent, then it should change what the stars look like. Specifically, if the light is bent together like a lens focuses light, it should make the stars look further away from the sun. Just like if you look at something through a magnifying glass, right? What is a magnifying? Where's my camera? A magnifying glass takes light and it focuses it inward. But when you look through it, because the light has been focused inward, it looks like it's coming from further away. So when you look through a magnifying glass at something, it looks bigger. This effect is actually called gravitational lensing. The gravity acts as a lens to focus the light and change the appearance of what's behind it. So if this is what these stars look like when the sun's not there, we take a picture of these stars 6 months ago or 6 months after the eclipse. Okay, this is what the stars look like normally. During the solar eclipse, they would look like this. I'm going to switch back and forth between these. Okay, sun not there, sun there, no sun, sun. You can see that the sun's gravity would act as a magnifying lens by distorting that light. Now, I am grossly exaggerating the amount of distortion. Light moves fast. The sun's not all that massive. So the size of this distortion was just barely detectable in the photographs, but it was there. We went out. The path of this eclipse actually cut across the western coast of Africa, across the Atlantic to Brazil. Expeditions were sent to photograph the eclipse from both sides of the Atlantic. And when we looked at those photographs, we saw that shift of those stars' positions, demonstrating that, yes, indeed, the sun's gravity does affect light. Not just that, but the sun's gravity bent that light by exactly the amount that Einstein's equations said it should. This is 1919, I think. It is at this point in history that Albert Einstein becomes famous, that the words Albert Einstein become a household name. It is not really his theory of special relativity from 1905. Scientists knew who he was, physicists knew who he was, his ideas were accepted, but it's not until this confirmation of general relativity that happens 1919 to 1921 or so that Albert Einstein becomes kind of the first celebrity scientist, the first scientist who regular people who aren't physicists would know their name. Nowadays, we can see gravitational lensing on much bigger scales. We have much better telescopes than they had in 1917, and we know that the universe is way bigger than they did in 1917. For example, we can look at light coming from distant galaxies. Every single white smudge you see in this photograph is a galaxy. It is a collection of hundreds of billions of stars located millions or billions of light years away from us. This galaxy is brightest because it is closest to us. So that galaxy is in the foreground, and all the other light you're looking at is coming past that galaxy. And what you can see when you look at the light coming from the other galaxies is you can see that it's all distorted, like it's passing through a curved piece of glass. This is one galaxy. Its image is stretched out. That's a galaxy. That's a galaxy. Its image is not long and thin and curved like that. The image of these distant galaxies is being curved, the light from those galaxies, I should say, is being bent as it passes by this close by galaxy. We can actually calculate the bending of the light by this galaxy and actually measure the mass of that galaxy, this galaxy that is, I don't know, probably 1 billion light years away from us. We can measure its mass by measuring how much it bends the light of those other galaxies as it passes by. Very cool. So gravitational lensing is real. Light is affected by gravity, which suggests that Einstein's interpretation of gravity as a geometrical property of space and time is correct. Which means that it is possible to imagine an object that curves space so much that even a beam of light would not be able to escape from it, that its gravitational pull is so strong that its escape velocity is greater than the speed of light. And Einstein's theory of special relativity from 1905 says nothing can go faster than the speed of light. It's impossible. It's actually nonsensical for an object to go faster than the speed of light in our universe. So as of 1930 or so, 1930, 1940, people had calculated that it is possible for an object to exist in the universe that would be a black hole. It would have such a big mass in such a small space and exert such a strong gravitational pull that light wouldn't be able to escape from it. It's actually fairly straightforward to calculate what would be required for this to happen. This is Newton's law of gravitation. Force is G times the mass of one thing times the mass of the other divided by R squared. We can use that equation to calculate the escape velocity of an object. The escape velocity of an object is the square root of 2 times G, that gravity number 0.0000667, times the mass of the object divided by the radius of the object. The gravitational pull of an object doesn't depend on its mass. It also depends on its radius, right? The smaller an object is, the closer, if you stand on the surface of it, the closer you are to its mass. So we took the Earth, right, and made it half as big, like the same amount of matter, but we squished it into half the size. The gravitational field on the surface of that object would be 4 times as big because of the R squared in the law of gravitation. So it's not just the mass of the object, but the size of the object that matters. And we can say, well, if we want to know what the mass and size of an object would be to make it a black hole, we just plug in c, the speed of light, for the escape velocity. We can calculate what we would need, how much mass and how small a space we would need to make a black hole. We usually express this in terms of R, the radius. For a given amount of mass, how small would we have to squish it so that if we stood on its surface, we wouldn't be able to get back off? We call that radius the Schwarzschild radius, named after physicist Carl Schwarzschild, who first did this calculation post-Einstein. Every object has a Schwarzschild radius. Not every object is a black hole, but every object with mass has a size that if you could squish that mass smaller than this amount, it would be a black hole. Okay. I can calculate, I can plug in a bunch of different masses of things and the speed of light and this little number G and calculate the Schwarzschild radius for different stuff. For example, the Schwarzschild radius of the sun. How small would we have to squish the sun such that if we stood on its surface, we'd have to be going the speed of light to get away? The answer is 3 kilometers, which is about the size of, I don't know, just a little bit bigger than RBC's campus, if you count the pecan grove and everything, right? So if you squished the whole sun down to 3 kilometers in size, it would be a black hole. The Schwarzschild radius of the Earth is 1 centimeter, which is, do I have a ball 1 centimeter in size? It's about the size of a marble, right? A little ball of clay here. It's about 1 centimeter in size. So if I could squish the whole Earth into this ball, into a ball this size, what I would have would be a black hole this big, that if I got this close to it, I wouldn't be able to get away from it again. It would have the mass of the Earth in this tiny, tiny space. You have a Schwarzschild radius. Your Schwarzschild radius is about 10 to the negative 25 meters. If we could squish all of your mass that makes you up into 1/1,000,000,000 of 1/1,000,000,000 of a meter, actually a tenth of that, 1/10 of a trillionth of a trillionth of a meter, you would be a tiny, tiny black hole. Now, that's really small, right? 10 to the negative 25 meters is about as much smaller than a proton as a proton is smaller than you. So squish you down to the size of a proton and then do that again. That's how small that size is. Really small. It's worth noting that a black hole doesn't immediately become a cosmic vacuum cleaner that sucks up everything in the universe. If we could somehow squish the sun down to 3 kilometers, oops, I accidentally went too far. I think it's okay to stop the share and go back to just me. If we could somehow squish the sun down to 3 kilometers in size, smaller than downtown Petersburg, just somehow reach into the solar system and squish the sun, the Earth would not change its orbit at all, because the mass of the sun is still the same as it was before, and the distance to the sun is still the same as it was before, and Mercury and Venus and Mars and Earth and Jupiter and Saturn would still keep orbiting that same amount of mass with that same speed at that same distance. It wouldn't immediately suck everything in the solar system in. What's different now, though, is that you could get very close to the sun, which you can't get very close to the sun now, right? The sun's about 100,000 kilometers across. You can't get closer than 100,000 kilometers from all of the sun. If you're standing right on the sun, you're 100,000 kilometers from the other side of the sun. You can't be 3 kilometers away from all the mass of the sun. That's what makes a black hole a black hole. We took all the mass of the sun and squished it down to 3 kilometers, so you could be 3 kilometers away from all of it. The gravitational pull of that thing would be so great that you could not get away from it, and it would be a black hole. Now, that is all calculations that happen on paper. We can take the mass of the sun, we can take the speed of light, we can take Newton's gravitational constant and compute that if you squished the mass of the sun into a 3-kilometer ball, what you'd have there is a black hole. That does not prove that there's ever any situation in nature where the whole mass of a star is squeezed down to 3 kilometers, or the whole mass of a planet is squeezed down to 1 centimeter, or the whole mass of a person is squeezed down to 1 trillion times smaller than a proton. That probably never happens. There's probably nothing ever that would ever happen in the universe that would squish the mass of a planet down into a 1 centimeter ball. But we just said in the last video that there probably is something that happens in nature that does indeed squeeze the whole mass of a star down into a ball that's just a few kilometers across. And that is the collapse of the core of a supernova. So there are 2 separate questions going on here. One, is the idea of a black hole a possible thing? Einstein's theory of general relativity says, yes, absolutely. By the way, the initial evidence for Einstein's theory of general relativity was this deflection of starlight by the sun's gravity. In the century since then, and we've just recently passed the 100-year anniversary of general relativity, right? General relativity has predicted countless physical phenomena that were not known about in Einstein's time that we have detected and measured since then. We've detected the effect of gravity on the frequency, a wavelength of light. We've detected the effect of rotation on the fabric of space-time, something called frame dragging. We have discovered that clocks run at different speeds in gravitational fields. A clock at the bottom floor of a skyscraper and a clock at the top floor of a skyscraper tick at different rates from one another. And this is not because gravity does something to the mechanism of the clock. It is because time on the ground floor of a skyscraper and time on the top floor of a skyscraper are different, because one of those things is experiencing a large gravitational force, a large curvature of space-time, and the other one is experiencing a small gravitational force. Gravitational waves, the periodic oscillation of measurements in space and time that travels through space like a wave, had been measured. Just had happened the year that I got this job, so about 6 years ago. The talk I gave when I came to Richard Blank College to give my job talk, to give my job presentation, that when you're trying to get hired, you come and you give a little lecture, right? The topic of my lecture was gravitational waves, which had just been discovered just about a month before. Gravitational waves are predicted by Einstein's theory of general relativity. We have observed them. We are pretty sure that Einstein's theory of general relativity at cosmic scales is right. That doesn't mean that it ever actually happens that something squishes a star down to 3 kilometers. It just means that if you did, what you'd have there is a black hole. It is then a separate question for astronomers to answer. Are black holes real? Do they really exist? Does that really happen in the universe? And if it does, how would we see them? After all, the whole point of a black hole is no light can escape from it. And we've said many times, all astronomers get to do is look at light. So if no light can escape from a black hole, how would we ever know that black holes are real? Well, black holes have a lot of mass and they affect the region around themselves. And so what we would look for indirectly is the effect that a black hole is having on its surroundings. So in our next lecture, we will talk about black holes and the evidence, the actual observational evidence that black holes are in fact real things that really do exist in our universe.